Okay, so I think you can hear me. So um, I will do a summary of sections 1 to 3, uh, kind of because it's last class before the midterm exam, and I didn't teach section 1, so I will give my own summary of the content of section 1, so I have a little bit my own perspective on these things. Um, so section 1 was kind of based, general introduction to the course, and we have had already some weeks of class, so you have a better idea now what we were doing and what kind of problems we were considering. So the upshot of section 1 was this criteria of which I call the kind of criteria of algorithm evaluation. So which consists in specification, semantics, which is primitives and cost, algorithm design, efficiency, and optimize. Okay, we discussed this in many situations, but so I will give some basic remarks about these aspects of algorithm design, and then you had a few very useful examples. So you had some algorithms for computing the Fibonacci numbers, which is very useful because you see very different ideas competing with each other, and each one has its own advantages and disadvantages. And then we talked about the master theorem, and we talked about polynomial multiplication, starting with the naive methods and then the continuous improvements until the algorithms by Cook. And then about we also talked a little bit about the matrix multiplication. So now this is Ada Lovely, if you do not know. So this is she is kind of known as the first programmer. Okay, so she was the girlfriend of Charles Babbage, the machine designer. And what should we say about specification? So here are some a list of problems of various types. Okay, and my understanding of this list is that we have to a little bit agree on what problems are useful to be considered by a computer or to be treated by a computer. I mean, there is I always like the quote by the painter Pablo Picasso. So you probably know him, so he's very famous. And once I read that, he said, computers are useless. They can only give you answers. Okay. So now, I mean, I do not want to completely agree with him. So I would not want to say that computers are completely useless, because if I thought that, I wouldn't teach the class. Okay. But there is something true in that. I mean, the point is that computers are useful for certain things, but not useful for many others. And we have to agree on what kind of problems should be treated by a computer. Now, here are some examples, like okay, find me a boyfriend or a girlfriend, and does God exist? And now, I mean, this can be a topic of a separate long discussion, but generally speaking, these are problems which cannot be specified in a way that it is helpful for a computer to solve. Okay, so then there are things like how many twin primes are there. Okay, so now this is a little bit closer to what a computer can do, because a computer can check you what numbers are twin primes, and it can output you a certain number of twin primes. Okay, but the proof, whether they are finitely or infinitely many, so no computer can find it. So mathematicians cannot find this proof. Mathematicians generally think that they better think about these problems by themselves and don't let the computer prove for them. So the question how you can use a computer to decide this kind of problem is very unclear. Right? I mean, there are ways to let computers prove theorems, or at least to check proofs, but okay, this is a separate topic. Uh, I do not want to. This is not the topic of our algorithm class. And since what I most like in this list are the last two. Okay, so this here, uh, and this these last two problems, they kind of pertain to diffusity of language, if you want. So basically, things that you can specify with ordinary language can be very imprecise, or in fact, as you can see in these constructions, they can even contain contradictions. So language is human language is a somewhat diffuse construct. It is not very strict. Okay, and so this allows for many inconsistencies. And so, for example, even if you try to make a mathematical theorem, you like logic, okay, you have to agree on certain rules that prevent you from constructing contradictions. Okay, so and this is a general problem with things that you can formulate in ordinary language. So these kind of things can inherit contradictions, and it is it is not clear how to have a computer examining this kind of question. So I mean, something that you should be checkable by computer must be strict in very restrictive ways. Okay, I mean, so if you write a mathematical paper and you make some error, then you can somehow assume that maybe if the error is not too big, the reader can fix it himself. But if you write a computer program and you make a small error, then the compiler doesn't care about this and does exactly what you're telling it. And then you need to spend several hours to find what error you made yourself. So I mean, this is the reason why we need to agree on some kind of somewhat strong formalism of what sort of questions we want to examine by a computer. I cannot make this super precise, but this is this is something that we have to agree in advance. So there are problems that can be examined by a computer, and there are problems that cannot be examined so well. So then we talked about, okay, this is about primitive operations, semantics, and costs. And there is some difference between algorithm and code. So in most cases, we were talking about algorithms without the actual implementation in some specific language. So, for example, I do not know assembler, so I cannot help you very much with this with this piece here. Okay, you know assembler better than I. But there was some way to make algorithms somewhat precise, independent of programming language, which we achieved with this pseudocode. Okay, so in many cases we have given pseudocode for some algorithms, and which is a little bit resembles this of C, but it's not exactly that of C. And from the pseudocode, you could in principle reconstruct an exact program by yourself. Okay. So, and then we were talking, so for example, here is the pseudocode for bubble code. Okay. And then we also talked about, we need to agree on primitive operations. Okay, so whenever we have an algorithm, we want to agree on what kind of operations we are allowed to use in the algorithm, what are they are supposed to do, and what is their cost. Okay, so and operations and bit operations, and the first example that you talked was this of multiplying integers by bits. Okay, and this is what is being done here is like paper and pencil multiplication, except that now it's not a decadic system, so all the digits are 0 and 1. This means when a digit of b is 0, then you simply omit the a, and when the digit of b is 1, then you simply take this word and then you shift it left. Okay, and then you have several copies of this word to be added, and then you get for two integer sequences as sequences of bits. So for two integers as sequences of bits of length n, then you can do this with at most n additions, but each addition consists of n bit operations, so you get to get all of n additions, but all of n squared bit operations. Okay, and then there was this something to whet your interest. We didn't prove this, but okay. Martin said about this recent algorithm of Haven van der Hoeven that you can this n squared can actually be reduced to an n times log of n. Okay, so that people thought about how to make bit multiplication of integers more efficient in terms of bit operation. So, and this slide here, I mean, I said this also in the beginning of section 2, but the purpose of this slide here is to demonstrate that the improvement that you achieve by improving the asymptotics of algorithms, basically. Okay, and what this tells you is that if you have a better algorithm, it will be probably 100 or 1,000 times better than buying a faster computer. Okay, so with even with the fastest machines, an exponential algorithm will not be able to do more than about 1/100. Whether you with the machines of 100 years ago, you would probably still be able to do faster 100,000 when you have a logarithmic algorithm or logarithmic complexity. Okay, so and this quote of Don Knuth, okay, premature optimization is the root of all evil. I mean, this, for example, means what Martin was talking about, that it doesn't help you very much improve the constants in the bubble sort, because the quicksort has a better complexity, and so you have to think about where to improve. Okay, so where would the improvement really improve the asymptotics and the efficiency of the algorithm? So, and then we were talking about this. We had this multiple times. We were discussing the asymptotic behavior of various functions, regarded mostly as a complexity functions. Okay, now this is now not much of a computer science. This is more or less calculus. I mean, what you should know are things like, for example, that logarithm grows slower than any positive power of n, particularly square root of n, and that the exponential, so 2 to the n, grows faster than any positive power of n. Okay, so logarithmic complexity is good, exponential complexity is bad. And we said that we were regarding functions up to constant. So we said that kind of f and g are asymptotically equivalent if and f less than or equal to c times g. So as you have seen, in many cases, when we analyzed algorithms, we were very negligent about constants. So everything which is constant in n for n going to infinity was regarded as up to constant was regarded as equivalent, which is not very precise, but for simplicity we have adopted this viewpoint. So and here is some picture of some growing functions. What to say about this? Okay, so this is the summary of some recent achievements in for example, primality testing. Okay, so one knows now that the fastest known algorithm of primality testing is Pauli log, so O log of 6. but for factorizing a polylog algorithm is not known. So power of log is not known. And so this is the basis of encryption. So all the modern cryptography algorithms, they use the fact that you cannot factorize huge integers efficiently. Okay. So and now there is this there was this this remark about complexity. So we discussed at this point the problem of powering, and obviously, if you multiply, say, an element in some monoid or wherever multiplication is defined by itself n times, that you can get the nth power. But it has complexity n, also O of n. Okay? But then we remark that we can do this by squaring the half of the power, and then we can do this logarithmically. So the the logarithmic powering algorithm. So you have a logarithmic powering algorithm where you take half of the power and then square. So you repeatedly square. And whenever the power is odd, then you multiply one more time by x. So then this gives you a logarithmic algorithm, and this lemma is a kind of a proof that logarithm is optimal. So for the powering problem, we can prove that log 2 or whatever. So the log of n is the optimal complexity, and this goes by simply giving some estimate on the size of the elements of the matrix. So this is a little bit, I mean, you will use now somehow that these are integers or polynomials or whatever, but basically the idea is that you can prove some exponential bounding the growth under in the number of multiplications, and then because of this you can prove that essentially log is the optimal complexity for power. So but this is an important point, so I will come back to it. So keep in mind that we have said at this point that the powering can be done logarithmically. And now this, I mean, okay. So now here this remark, which is so this story here is you can reduce powering, let's say, of real numbers to a finite number of operations if you allow exponentiation and logarithm and multiplication. Okay, but you must be careful. So I mean, so for example, he's written in some monoid. Okay, but then when x is an element in a monoid, you have to say what is ln of x, and this becomes a more complicated problem. So this calculation here has its own problems. Certainly, if you say if you allow real numbers, you can do like that. Okay, and so when x is a positive real number, you can do like that, but then you have to this means we allow as primitive operations to take exponentiation and logarithm. Okay, but how to do this for other monoids is a more complicated question. So I mean, what he wanted to say in this example is that, and we had it a few times also here, that when you allow more power for primitives, then you can of course reduce complexity, because the complexity is encapsulated in this more powerful primitive, so in the capacity of these primitive operations. Okay, so now this example was very good because it is a very well-known problem and simple problem, and there are several approaches to it. So the Fibonacci numbers are defined recursively, and you can do this using the recursion, and you see that the number of operations is at least as much as the value of the Fibonacci number, which is exponential. So this is so this means that this is not good. And then you saw that you can save this effort by memorizing the previous two Fibonacci numbers. Okay, so and then you immediately see that you can do this also in O of n. Right? So we didn't talk about very much about the bit cost. So let me skip. So and then we notice that there is another way. So we notice that this recursion for the Fibonacci numbers, which is implemented here, can be written as matrix multiplication, from which you get that you can calculate the Fibonacci numbers as the power of a matrix times the vector, which essentially you can take the vector 1, 0 and then power the matrix 1, 1, 1, 0 and then multiply. And since you know that matrices as elements in some monoid can be powered in logarithmic time, you immediately get a logarithmic algorithm. Okay, because you can power the matrix in logarithmic time. So with this you get a logarithmic logarithmic algorithm for the Fibonacci number. And then there were two extra formulas. You can actually make the formula for the Fibonacci numbers. So this recursive formula, you can make it explicit by using the golden ratio. That's actually the inverse of that, but okay. So so this means, in principle, that you can you can say something like when n is bigger than, let's say, 3 or whatever, then this number here is less than 0.5, and then you can simply take 5 to the n divided by square root of 5, and then you can round it, okay, to the nearest integer. Okay, and this will give you a formula for the Fibonacci number. This is another way of seeing this is to okay. So you have this explicit formula, and you can, if you want, you can reduce the problem of calculating Fibonacci numbers to the calculating powers of a real number. Okay, and if you want to be even shorter, okay, the powering of a real number now can be expressed as exponential of n times logarithm. Again, so this means if you want to write a Fibonacci number, so Fn will be phi n over square root of 5. So you use this formula here for phi n, and then you round it. So let's say something like this, integer of this plus 0.5. This is greatest integer. Okay, so you get, and then you get actually an algorithm which is not logarithmic, but it actually is all of 1. Okay? But I mean, I warn you. So okay, of course, again, this means if you allow these very powerful constructions with exponential and logarithms, then you can reduce it to actually to all of 1 complex. But I mean, I must warn you. So if you want to implement this in C or C++, and you write something like, I don't know, float, you write something like this: float phi is equal to 1 plus square root of 5, okay, over 2 or something like that. Okay, and then you try somehow to power this phi. I mean, you must be aware of all the problems with this data type. And I do not have now time to discuss all this. So, I mean, there are very known precision problems. So you see, if you want to calculate it in this way, you have to calculate this huge number potentially. When n is large, this is a huge number. You have to calculate this number to the precision of 1. Okay, and this data type will be utterly insufficient for that. So if you're interested in how to make real computation exact, then this is one of the main topics on which people are working in our lab. Okay, so you're welcome to come to our lab, and Professor Martin will have enough things to choose to give you to work on. Okay, so this means in this formula is, I mean, as nice as it is in theory, there are a lot of practical problems with using this on a computer, and this is something that you have to be aware. I do not want to discuss this too much because we don't have time. I mean, I'm doing a summary lecture now, but this is something that you have to consider. Okay. Similar is the story. Similar is the story with integers. Okay, integers do silent overflows. Okay, and so for example, if you type integer and you try to use the recursion, then you get Fibonacci number is equal to minus 300 million, and then you have to see what went wrong. So, I mean, there are many problems of influence. There's a big difference between this kind of mathematical formula and how to make it work on a computer. But okay, I don't have the time to discuss this too much. So now we discussed this master theorem, which we used this several times for estimating complexity of functions, for example, which call themselves recursively. Okay, and basically, so this recursion depends on these three parameters. Okay, now this depending on the values of these three parameters, you get a complexity estimate for let's say growth estimate for this function f, and we use this as a complexity estimate for some type of algorithm. Okay, important is here that there is only one on the right side. There is only one value of f. And so when f is called with different arguments on recursively, then we cannot use it this way. But there are some situations where we were able to use the master theorem. So it's a useful tool for estimating the growth of function and then some complexity of algorithms. And then we have this long multiplication. So the question was about multiplying polynomials. How can we make multiplication of polynomials efficient? And so what we said is that you can of course do so what is written now here. So what is written here is the naive algorithm. Okay, if you want a kind of paper and pencil multiplication. Okay, but we saw that we can do this a little bit better. So we broke our polynomials into two halves. Okay, when the n has degree capital N, we split it into the first half of the coefficients and second half. Okay, and then we said we can build the product by multiplying these halves, where you must be careful. So C0 will go from here to here. So C0 will cover all these coefficients. C1 will cover all these coefficients, and C2 will cover all these coefficients. So there is an overlap. But the overlap doesn't create any problem. So you simply add coefficients in the correct degrees, and even if coefficients overlap, you simply add them in the proper place. So this wouldn't create a problem. So what creates the complexity in this situation is the number of multiplications. And if you do this now in the usual way, you have 1, 2, 3, 4 multiplications. Okay, so and okay, you plug it into the master theorem, and then you see that this is O of n squared. So this okay, with this you gained nothing. But there was done this Karatsuba variation of that calculation, which allows you to build these numbers C0, C1, C2. Yeah, so these numbers C0, C1, C2 can be calculated from A0 and A1 and B0 and B1 only using 3 multiplications. So you reduce the number of multiplications. The additions always give you something which is O of n. Okay, so the additions do not matter up to constant. so the multiplications decide the main part of the complexity, because when you reduce this, when you reduce the number of multiplications, then this factor here reduces, and then when you plug it into the master theorem, this reduces the exponent of the n. Okay, so I don't know, was it written somewhere? Or, so you get n to log 2 of 3, okay, instead of n squared. So the number of multiplications reduces the exponent of the n. And then there was Thum, who said, okay, so when you can do this in groups of 2, why can't we do this in groups of 3? Okay, and then I have I have 5 C0 until C4, and I have 3A1 until A2 and 3B1 until B2. I do this in the ordinary way. I can do this certainly with 9 multiplications, but this is not. I want to reduce the number of multiplications, and we found that we can do this with 5 multiplications. So taking linear combinations was not important for the complexity, and then so by Thum, we can now reduce the size of the polynomials by 3, and we have 5 multiplications. Okay, and this will give you now, I think, so it will give you n to the log log 3 of 5. Okay, which is, so, and this number log 3 of 5 is less than log 2 of 3. So this means you can further reduce the exponent by using this formula. Okay, but now these formulas become more complicated. You have to use fractions and so on. Then the number of additions also grows. So this means even though we are very sloppy about the constants, okay, these constants also increase. So the constants that come in this O of n, they increase. And then there was then the further improvement of Cook. Okay, and what Cook did was so what Cook did is say, why can't we split it into into groups of small n and small m. So when you have polynomials of fixed degree, small n and small m, and here I think we better use like this. You can multiply, or you can find out the product, the coefficients of the product, by evaluating the product by simple multiplication, and then you know values of the polynomial, which is the product, and you can reconstruct the coefficients from the values using this inverse of the van der Monte matrix. Okay, so you have to fix values x0 to xk, which are distinct and they are fixed, and you can reconstruct the coefficients of the product from values of the product, which you evaluate in this way by multiplying with this van der Monte matrix. Okay, so and so this of course works when n and m are fixed. So small n and small m are fixed here. So this number and this number are fixed. Okay. But of course, you want now to multiply polynomials which are very big, not a fixed degree. Okay, and then comes this idea. So when you have a polynomial of in x of degree capital N, then you can regard this as a polynomial in x of degree small n, but you have to change x to the power n over n. So what stands here? Let's say write. So you write x tilde is x to the capital N over small n. Okay, and now here stands x tilde to the power n minus 1. Okay, and here stands x tilde, and here stands x tilde squared, and etc. Okay, and the coefficients of this polynomial, now the self polynomial in x with degree less than equal to n over n. So these polynomials here, these are polynomials in x, and the degree of this is less than equal to capital N over small n. Okay. So, and what you do now is you try to multiply these two polynomials as polynomials in x cubed using this construction here. Okay, so using this Vandermonde, construction. So you regard these polynomials as polynomials in x cubed. Second one. So the second is now of degree capital M over small m. Okay. So in degree small m in x over capital M small m. And now you use this construction here, but except that now this a of x0 and b of x0, they are obtained by only substituting values for x cubed. This means that these themselves are polynomials which are some linear combination of this ai. And then so although these are combinations, when you substitute something, these are linear combinations. So what stands here in this multiplication is some linear combinations of this times the linear combinations of the BI. And this means that you can reduce the number of multiplications to k plus 1, which is n plus m minus 1. Okay, and everything else is linear combination. So you take linear combinations of those, then you multiply, and then you have to multiply with this Vandermonde matrix, the inverse of that, okay, which you calculate in advance. And then this means, so now this right. So and then this means that so when you do this, you can use the master theorem to get the complexity of this algorithm. So important is that you get n plus m minus 1, so k plus 1 products of polynomials whose degree of products of polynomials whose degree in the one is the degree is n over n and the other one is m over m, because these were the degrees of these ai's and bj's. They come here into this. So this is the degree of AI, and this is the degree of bj of all of them. So you get some multiple times this recursive course, and then you get something which is linear in capital N and small m for fixed for capital N and capital M for fixed small n and small m. Okay, so this is what you get from all these linear combinations and that stuff. Okay. But when small n and small m are fixed, this is linear in capital N and capital M. So you get something linear plus this the complexity of this recursive calls which come in this multiplication, and then you can see, let's say if you put n and m equal and going to infinity, you can see that you can get from this n to the power 1 plus epsilon for every epsilon bigger than 0. Okay, so you get a whole cascade of algorithms, each one with better efficiency. Okay, but of course the point is not to let epsilon go to 0. So this doesn't really make sense. So what you should do is, when you're in practice, when you're given two polynomials of degree capital N and capital M, you should choose small n and small m so that this is the most efficient. Okay? But making small n and small m arbitrarily large will not help you. Okay? So you have to choose them properly. But theoretically, theoretically, you could have with this an algorithm which is all of n times power 1 plus epsilon for every epsilon go bigger than 0. So this was the Cook's cascadation of the tomb algorithm. Okay. So not enough time to talk more about this, but I think you had this in your class in more detail. So, and the last piece was that somebody attempted something similar for matrices. Okay, and now when you split a matrix into two pieces, you of the 2 by 2 blocks of the matrix, and somebody found that you can do this actually with 7. But so this means if you to put it into the master theorem, you will reduce the exponent to log 2 of 7 in matrix multiplication, which is better than cubic. So cubic is obviously the naive algorithm. And then there was this announcement that the current world record for lowest exponent of n is held by Francois Legal 7 years ago, which is 2.37. Okay, but the question is this optimal? It seems unlikely, but for example, one has not found a similar cascade of algorithms like for Cook's algorithm for matrix multiplication. So, for example, one does not know whether you can make it in n to the power 2 plus epsilon for every epsilon bigger than 0. If you find such thing, you will get very famous. Right? But so this is not known. So the current world record is 2.37 for exponent. So okay, this is what we said about. So then okay, here I took over, and now we were talking about these things in considerable detail. So we were talking about searching algorithms in section 2. And then we will talk about various types. So we were talking about, so we are talking about various types of searching. Okay, and the first one was the naive linear search. Okay, we said you can do this for every arbitrary array, and the runtime is linear, and simply you check every element. You can't do any better. Okay, then we talked about find between which neighbored elements it is, and in order to something doesn't work. Okay, to annotate, very fine. So so in order not to have problems, we said we make a large final element and a small initial element, so that there is always an n which satisfies this, so that there is an output. But this, if the array is not sorted, this is ambiguous. Okay, so this is also something that I said you have to consider. Is the output unique? Because if the output is not unique, then you may have different algorithms which are both correct and give different outputs. So and again, so this was linear time, and then but I said that if the array is sorted, then you can improve it. So for a sorted array, you can always test against the middle element. So this was important when you can test this element y against the middle element, and then you can restrict the size of the area on which you look by 1/2, and then you get logarithmic complexity. So searching in sorted arrays can be done logarithmic time. Okay. So, and then we discussed several issues of uniqueness. So the problem here was, when I'm giving an array of elements, how can I decide whether two elements are equal or not? And the first algorithm, unique one, was simply test every pair, which is quadratic. But if you have a sorted array, then you can do better. In a sorted array, testing uniqueness is much easier, because you need to test only two neighbored elements, and then this becomes linear complexity. So in a sorted array, uniqueness can be done in linear time. And then we discussed several modifications of that procedure. So one was, if you have elements which are integers, then what we did was we used these integers and indices in a database. Okay, and so we declared a database of booleans with values given in with indices given in the set of values 0 to m minus 1, and present m or present x means was x previously encountered as one of these xi. Okay, and then if you do it this way, then you can do this in linear time. Okay? then without sorting the array. So you have a linear time without sorting, but the problem is that you have this huge memory consumption. So if m is very large compared to n, then you have to do all this initialization and memory consumption by yourself, and this becomes very unpleasant. So and to reduce this memory consumption, I was discussing in very detail this hashing method. Okay? Which, so what is the idea one more time of this hashing? So you want to reduce the memory. So you do not want this whole chunk from 0 to m minus 1 because m is large. You choose a certain smaller number p, and you reserve only an array of p elements 0 to p minus 1. Using xn itself as the index in the array, okay? You try to use xn mod p, or let's say a hash function applied on the element xn is you try to use it as an index in this array from 0 to p minus 1, and you use mod p in order to get something between 0 and p minus 1, so that this is an index here. Okay, so you have then this hash function. Okay, now what was the what was the problem? So one problem was first that you cannot store xn itself as the index because you lose information about xn when you apply the hash function. You can have different xn with the same hash function. Okay, so this means you cannot store simply Boolean into this array y, but you need to store xn itself, and this is why you get something like here. You have to assign xn to an element in this array y, and y is now an integer, not a Boolean. So this is the first thing, and the other thing is that you have to avoid collisions. Okay, because now you can have different xn with the same value of the hash function, and then you cannot overwrite one value, one entry in y with another. This is something that you have to consider. And then we said we simply skip over all previously written entries until we encounter one where we can write it. And then we discussed, so the memory consumption of this is all of p, okay, because this whole thing does not appear anymore in the memory. So the only thing that appears is here. Okay? So what was the runtime? The runtime was, it depends on this loop here, which goes over written entries. Okay, so this here it depends on the number of collisions, and this is why I said you should choose the hash function so that for many different xn you have as many possible different values of the hash function. And this is why, for example, it is useful that p is prime. I said that p bigger equal to n is imperative because otherwise the algorithm may not terminate because your database may get full. But P is not necessary that p is prime, but it is helpful because it will create very many different values of the hash function. They will reduce this collision, and this will reduce the complexity. So in the optimal case, it would be linear, but in the worst case, it will still be quadratic. Okay, and now here was some example about how these elements are written into the array consecutively depending on the value of the hash function. So you use the value of the hash function as an entry point where you start looking for a place where you will write the entry. You do not write the entry just exactly at the index given by the value of the hash function because you can have this collision. So, and then we talked about order statistics. Now, as you have seen in section 3, it was very useful to understand what the order statistics are. So the order statistics was if you're given an element, a number k between 1 and the length of the array, find the index so that xm has approximately k smaller elements. Okay, this is what more or less this was supposed to do. If you assume that all the elements are distinct, you can simply write k is equal to that. Okay, in general, you have to use like this, and okay, you must be careful that this m is not this m is not unique when there are equal elements in the array. And then there were two algorithms which we discussed. One was the quadratic runtime naive algorithm. Okay, so this was simply evaluate these numbers for every m, and then if k is between the two, then you simply can output m. Okay, so there was a quadratic time naive algorithm, and then we said that if you are the array is ordered, then you can simply do, okay, then there's actually nothing to do. You can simply return k itself. And you have to see. So these were the two order statistics algorithms that we discussed at the time. I also discussed the effect of sorting, but I do not want to get to this now. So simply remember the things the way that they are written on the slide. So we had these two runtime, median algorithms. We said later that there is actually a linear algorithm for non-sorted array, but I will come to this a little bit later. So, and then we did this range counting problem. So given two elements x and x prime, find all the elements in between. And we said we can do this in a naive way linear time, but if you use the binary search, we can reduce it to logarithms by simply calculating the left boundary and the right boundary, and then locating the position of the left and right boundary, and then simply returning the difference. So the binary search can be used to speed up the 1D range counting if you have a sorted array. Okay. And then we were talking about these binary trees. So that there is a way to represent sorted elements more efficiently than in an array, namely in these binary trees where you have a split. So every node which is not a leaf has a left node and a right node, and this splits the elements into two halves, and then this continues until eventually you land in a leaf, and every node which is not a leaf contains all the elements above. So this is why, for example, so 12, 14, and 17 are above this node, and then this node contains some information about 12, 14, and 17. Okay, when you want to count, it is enough to store here the number of elements and minimal and maximal elements. Okay, and then there is an algorithm whenever you're given x and x prime to descend for x and for x prime into this tree to find where is x and x prime in this tree, and then you to add the elements corresponding to the leaves whose to the nodes whose leaves are all within x and x, between x and x prime. So, for example, in this case, there were slides in the old version of the node, but so, for example, this node is there, this node is there, this node is there, and this node is there. Okay, no. So x prime is here. Okay, so this. So, and then you, by adding the information that corresponds to the red circled nodes, you can get this number. Okay, and the important point was that you have to store some extra information into these intermediate nodes because you do not want to descend until the leaves. If you descend until the leaves, you always have a complexity which is proportional to this k, and you want to avoid it. You want to have log n complexity. So this is why you need to store this extra information. So, and then okay, I said that so you can modify this for determining the set by itself, not only the number of elements but the elements themselves. And then also said that you okay, with some modifications you can do this in a nested way. So you can do this for two components. So for pairs of components, and then you have to nest the tree. So you have a binary tree. I didn't make it into every detail, but more or less I explained what has to be done. And in section 4, data structures, which comes after the midterm exam, I think you will discuss in more details how to work with these binary trees and to see what is the advantage of these binary trees as compared to arrays. For example, that it is more efficient to add elements into a binary tree so that it remains sorted. Okay, if you do this in an array, you may have to copy half of the array. Okay, but in binary trees, this can be done. This can be done faster. We are talking about sorting, and there was a lot to say about sorting. So we discussed various types of sorting algorithms. And again, with respect to this criteria like specification and semantics and cost, design analysis and optimality. Okay. So what did we say? We discussed several types of of algorithms. So our goal is, if you have a sequence, then find a permutation so that the permuted sequence is ordered, which means x pi 1 less than equal to x pi 2 until x pi n. And mostly we were using operations which are swapping, in index integer arithmetic and comparison. And in certain cases, we said we need to copy elements, so we need external memory. So the first argument, the first algorithm that we had was the bubble sort, where the idea is that you compare two neighbored elements and move the bigger one to the right. Okay, and this is what is done in this animation. So this is what this inner loop does. And after this is done, the rightmost element is the largest. So for example, this 8 now will go to the right, and the 8 and 4, 8 will also go to the right. And then after this loop for k is finished, you know that A is the largest element, so you leave it on the right, and then you simply start doing this until the second last element. For all the elements that are here, you compare neighbor pairs. When the left element is bigger, you swap. So 6 is less than 7, so you don't swap. 7 is bigger than 2, so you swap. 7 is bigger than 4, so you swap. And then you you know that 7 is the biggest among the others except this 8. Okay. So and now when you do this, so m is the index of the element that becomes the black box at the end of this iteration over k. So and when you do this until 2, then you will know that 2 to the n is the largest element except those which are to the right, and then it is enough. So then the array sorts. So this is what the bubble sort was doing, and we saw that the runtime is quadratic. So you always have a quadratic number of comparisons. So okay, so this was the first idea. Then we discussed the select sort, which is a similar, which was a similar idea, and uses, so it goes from among the unsorted arrays, unsorted elements, and remembers the index of the smallest one that he finds, which is this red one, and the blue one is the one over the element that he checks. And whenever he finds something which is smaller than the red, then he makes the red to that. And at the end, you swap the first non-sorted element with the smallest element among the non-sorted elements, and then you get a sorted array. And this is also quadratic. So, and then there was this insert sort, where the idea is that when you sort this from the left, you have a left piece of sorted elements, and then you consider the first element which is not sorted, which is this red box, and it is written into this variable y. And at the end, you try to insert this first element so that one more element is sorted. So 1 is less than all the 3 black boxes. This means it has to go to the left. Now 8 is bigger than all the 4 black boxes, so it remains on the right. 7 is bigger than 4 of the black boxes, but not the 8. So you have to move the 8 right and insert 7 properly. Okay? And now when you do this until the end, then you will have a sorted array. Okay, so it's not difficult to see that this algorithm is correct, because after m iterations, the first m elements will be sorted, and the complexity is, worst case complexity is again quadratic. It depends on how many elements you have to shift. If the array is sorted, simply checking that it's sorted would be the fastest, and it would be O of n. But the worst case complexity is O of n squared. And then we were discussing the merge sort, where you have to split your array into two pieces of the same size. Then you work recursively, and then you recombine. Okay, and so then we had, okay, the master theorem will give you very easily that this is O n of log of n, which is much better. Okay, so this was so far the fastest algorithm that we got. The only problem that we had in this merge sort is that you always need this copying. Okay, because you do not know whether everything on the left is less than equal to everything on the right. And when you sort these two pieces, you have to recombine them. And this was this code here. In the animation, it was done from the left. I said that this was done from the right, but it doesn't really matter. So you always need this recombination, and this always costs you some extra memory. But the complexity is good. So if you can afford a little bit of extra memory, you can do in this better complexity. And we said that n log of n is the total amount of memory required, but if you can reuse memory, if you do not parallelize, if you call this after that or this after that, then you can reduce the memory to O of n. And then we talked about the quick sort. So now, I mean, you see, I do not have enough, my time is always too little to recall this story in every detail, but I mean, I talked about it the last couple of times. So what happened in the quick sort? In the quick sort, that everything on the left is not necessarily less than everything on the right. And we fixed this problem by choosing a pivot element, so this S, and then doing this piece here, which was kind of which is a partitioning call. After doing this iteration here, everything left of S is less than S, and everything right of S is bigger than S. Okay, and then when you have this, then you can simply call quicksort on the two fragments until this division A is equal to B, and the two recursive calls will sort the whole array correct. Then you don't need to copy. But the problem was that you do not know where this A and B will land. These pieces left and right of S can be, one can be very small, the other one can be very large. And this gives you the worst case complexity, which is quadratic. Okay, you can choose the pivot element randomly. Okay, you can choose it randomly in some way, but okay, so no matter how you choose it in this way, you cannot guarantee that A and B doesn't land very left and very right. So, and then we try to fix this problem. So we try to remove this to fix this problem by saying, if I can choose my if I can choose my S, so that after doing this code here, okay, I have here at least an epsilon times n, okay, and I here at least epsilon times n for some epsilon which is between 0 and 1 fixed, then I can do better. So I can avoid that this S is too far left and too far right, at least an epsilon of the size of the array. Okay. And then we said when you can achieve this, then actually you get the O(n) log of n complexity, which you wanted. And the proof was, you cannot use master theorem, but with this ansatz this is not difficult to see. So and to fix this issue, we try to design an algorithm that allows you to choose a pivot element S, okay, to choose a pivot element S, okay, where you can have epsilon is equal to 0.3. And we were discussing about this algorithm in great detail. So, I mean, in as much detail as our lecture time permitted last time. So what did we do? So this was an intricate construction. So we we first needed the split. So the split was the one more time. So let's see. I probably have enough time to draw as much. So the split was, if you have an S, it will move it somewhere, and everything here will be less than S, and here everything will be bigger than S. This is what the split does, and I said instead of split, call this better partition, because on some slides it was called split partition. So this is we need this piece, which was part of the quicksort algorithm. Okay, and then we need the order statistics. And by assuming that not there are no distinct elements, which is only a small technical problem, we said that actually there is a unique element for every case, so I can simply write it this way, so that there is no problem with this ambiguity in the order statistics. So we need the partition, and we need the statistics. And what we wanted to output is the median of 5 medians. Okay, so you split your group, your array n into groups of 5. You take the median of each of these group of 5, and you take the median of these medians, which are the black dots. And then we argued that the median of the medians will be at least 30% away from the smallest and largest element. So because all the elements which are red are bigger, and all the elements that you have here, so one more time, okay, all the elements here, okay, they will be smaller. So this is why the median of 5 medians is a good choice of the of a pivot element for the quicksort, which satisfies epsilon is 0.3. Okay, so now how did we do this? This was really, I mean, you need an idea for that. Okay, and the idea is that you use two pieces. The one was the order statistics, giving you at the end a linear time order statistics for an unsorted array. And the other one is this approximate median, which is the median of 5 medians. And the order statistics needs the approximate median in order to restrict the size of the area on which it calls itself recursively. Okay, so this is what written here: proceed to the left accordingly. This results in a recursive call, and by using the approximate median, you can bound the size of the piece on which you call it recursively to 0.7 times the size of the original area. This is where you get that. Okay, and so you need the approximate median to control the size over which you call itself recursively. And the approximate median now that's what it was what you were supposed to do. You determine the groups of 5. In each group you find its median. We said it doesn't really matter up to constants what method you use. You can simply sort it. Sort in any way, bubble sort it, then take the middle element, whatever. So you can do this, and then you call the order statistics on this area of the black dot. So what you get in this the median of 5 the 5 medians is an array, is this area of the black dots. Okay, so of these stick dots. Okay, and you forget about the other elements, and then so this has size n over 5, and by calling up order statistics with a half of it, which is n over 10, you get the middle elements of this element. Okay, so then you get this, which is what you want. Okay. So this means, and now you have this recursion where every algorithm needs, where every procedure needs the other one. And we analyzed with some with some effort, we're trying to analyze the complexity. And this leads to these two formulas. And the important point one more time about these formulas was that 0.2 plus 0.7 is less than 1. Okay, and this allows you for a linear time. And then we argued using these decision trees that as long as you only use comparison, you cannot sort with less than O of n log of n, because every decision gives twice as many possibilities, and the number of possibilities you have at the end must be n factorial, because every permutation of the area must be achieved in some comparison must be at least log n factorial, which is O n log of n by Stirling's formula. So this for comparison sort, we had this optimality, and then we said there is some way of sorting other specific data types like integers by do not comparing them, but rather simply using them as indices in an array. This was a little bit like this database uniqueness problem, okay? Where now the key is an integer and you do not compare the keys, you simply use them as indices in an array. Okay? And then we thought that one can be done in linear time, but with some, by abandoning the comparison principle. And similarly, you can do with binary strings. And there was a question in the chat: what about m is not fixed? M is fixed. Okay, I said this last time. I checked my recording, so I did say it, but I did say it only once, so now I say it again. Right? This lexicographical order of binary strings works for fixed m. Then you have this recursive algorithm, which is similar to quicksort, except that the splitting is done with respect to the mth bit, and everything where the mth bit is 0 goes left of everything where mth bit is right. Okay, and this again can be done in linear time with respect to the array when the bits, the number of bits is fixed. So, and it's useful when m is small compared to n. Okay. So, and then we discussed the sorting networks for parallel sorting, that you can design a sorting algorithm in terms of these primitive gates, and whenever two elements are wrongly sorted, then you can swap them. And then we said that you can unroll algorithms like the bubble sort into a sorting network. And then we discussed, so bubble sort has quadratic complexity, means the number of comparisons is quadratic, so the number of these gates is quadratic. But if you parallelize it, assuming that you have an unlimited number of parallel CPUs that you can work on, then you can do this in linear time. And then we finished with this outlook that, in fact, the fastest algorithms were n log of n. So this is what we learned, but actually you can parallelize them to O log of n. So I mean, you can have n times log of n gates into log of n vertical positions split. Okay. So okay, and now I mean it's a little bit I'm a little bit over time, but I think more or less I made it. So this was the kind of the story for sections 1 and 3. Okay, and now I think so you should be prepared for your midterm exam, and then Martin will continue with this lecture after the midterm exam in 2 weeks. Okay, thank you for listening, and see you maybe next semester or whatever.